Hello guys, so for this problem we're going to consider like any set X, so let X be a set, and for this X we're going to consider like two possible topologies. One topology is going to be tau of C and another one is tau infinity. So we want to show that tau of C is going to be for sure a topology, and tau of C is going to have the following description. We're going to say that element A belongs to tau of C if X minus A is going to be countable or is going to be all of X. So to have a picture in mind, you're going to consider your set X. You will take some subset A. You're going to take its complement. So complement is going to be all elements that doesn't belong to A. And you're going to ask, is X minus A is equal to X itself, or is it countable? If yes, then from here will follow that your subset A is going to belong to your topology. And for our second tau infinity, we don't know if it's going to be a topology or not. So we will need to figure that out after we're going to done with tau of C. So let's show that that is actual topology. Remember, for that we need to show two properties. The first property, we need to show three properties, but I'm going to show only two properties, and the third one is going to be as a homework exercise. So let's take an empty set and a set X itself. Then we want to show that it belongs to tau of C. And the second property that I'm going to show that if we're going to take like any collection of AI, where AI is going to be a subset of X, and by any collection mean like it can be either finite, countable, or uncountable, or I'm going to run my index I over any like index set. Then if I'm going to take the union of AIs, then the union of AIs must belongs to our topology. Or in other words, the union of I that runs through I of AI is going to belong to tau of C. Okay, let's first show the first property. So let's see why empty set belongs to tau of C. So empty set belongs to tau of C because if I'm going to take my empty set, then what do I need to do? I need to check what is my X minus empty set. But my X minus empty set is going to be X itself. And since the requirement that X minus A can be equal to X, then from here follows that empty set belongs to our topology. In other words, that's why we need that requirement, because we want our empty set to be inside our topology. Okay, and what about X? Why X belongs to the topology? In this case, if I'm going to take X minus X, that is going to be an empty set. And you know the set that doesn't have any elements is countable because any finite set is countable. So from here will follow that X also belongs to topology. So we got that empty set and set itself in our topology, and we're done with the first axiom. Okay, what about the second axiom? For the second axiom, let's take the collection of AIs. So for that, we need to test what is going to be our X minus the the union of collection of AIs. But to figure that out, remember this picture. If we're going to take the union of two sets, A1 and A2, then we're going to have that green region. So the complement, or in other words, the X minus the union of two sets, is going to be this blue region over here. And you can see you can get that blue region if you will take your A1 and consider its complement. Let's take it with yellow over here. And then you're going to take A2 and consider its complement, which is going to be with orange. Then we are exactly going to get the blue region if you're going to take their complement and intersect them. Or in other words, X minus the union of AIs is going to be equal to the intersection of X minus individual AI. And again, one set minus other set, it means that the element that belongs to the set, they just don't belong to the set AI. Okay, and what do we know about here? We know that since by our definition, when we're going to take our AIs, we require that our AIs belongs to our topology. So since our AI belongs to our topology, we know that x minus I is going to be countable, or all of x. But if we're going to consider that all of them are going to be countable, and you take in the intersection of the countable sets, so think about this in the following way, that you're going to take x minus a1, and then you're going to produce this set over here, but taking this countable set and intersecting this countable set with other countable sets. So, but intersection, when you have like your set and when you're going to intersect, for example, with some set, then you can see you're going to get a smaller part of the original set. So that's why the smaller part is going to be at most countable. And that's why this intersection over here is going to be at most countable. And since it's at most countable, then our requirement is satisfied. So we know that this intersection is going to belong to our topology. And since certain intersection is going to belong to topology, since intersection is at most countable, then we can see that our union of AIs is going to belong to our topology. Okay, and I'm going to just state the last axiom, but I'm not going to, not axiom, like the property that we need to check, that I'm not going to prove, that if we're going to take any collection of AIs that belongs, sorry, not any collection, we're going to take a finite collection of AIs. So in other words, our index I is going to run between, let's say, 1 and some natural number n. Then I want to show that finite intersection of AIs is going to belong to our topology. So feel free to check it on your own, and please let me know if you have any questions. Okay, and we're done with this first part. So this part is check. Let's try to figure out this one. If we're going to consider tau infinity, if that tau infinity is going to be a topology. So first, we need to observe a couple of things. So what is my tau infinity? It's going to be all subsets of x, such that x minus u is going to be infinite or empty. So we are not allowed to have x minus u to be finite. So that's why we included empty as an additional requirement, because we want, remember, for the first, according to the first property, that empty set and x must belong to our topology. And here you can observe, since we want our empty set belongs to our topology, then from here follows that x minus empty set is infinite or empty. And since empty is redundant, then we have the requirement that our set x must be infinite. And then what we can conclude? We conclude the following. Since x is infinite, then what we can do, we can take some element a inside our x. So let's just sketch a picture. This is going to be my x, and then I'm going to take some element a here. What can I say about that element a? Let's consider x minus a. And what we can say about this x minus a? X minus a must be infinite. Since it's infinite, then from here follows that my element a, the subset, is going to belong to our topology. Since our element belongs to our topology and we didn't have any restrictions, so we can choose like any element a. So you can say for any a that belongs to x, we have that a belongs to our topology. But if a is going to belong to our topology, what we can do? We can take the union of elements a that belongs to x, and as we showed in our for our first part, for our problem, we can see that that also must belong to our topology. But here we're going to do one trick. Let's take some element b, and what we're going to do, we're going to fix this element. Fix this, and we're going to take the union of all elements except a that doesn't equal to b. And you can see that this set over here, from one side, is going to belong to our topology. But from the other side, we must have that x minus union of A belonging to X and A doesn't equal to B must be either infinite, empty, or all of X. But you can check that this set is actually going to be equal to B itself, because this union means we're going to list all elements except one, and then we're going to subtract that set from original set X. So the only element which is left is B. So from one side it belongs to infinity, but from the other side this B is not infinite, is not empty, and is not all of X. So that's why we obtain a contradiction. And since we have a contradiction, that proves that our claim, not a claim, that question is answered, that if tau of sigma, sorry, if tau of infinity is a topology, and the answer is no. And the answer is no because we have this contradiction over here. So in other words, since the set X must be infinite, and each element itself as a subset is going to belong to our topology, then if you're going to take collection of all elements except one, it must belong to our topology, but it doesn't belong to our topology because X minus that union is going to be a finite set that is not allowed by definition of our topology. And we are done. Okay guys, please let me know if you have any questions. I hope you enjoyed this problem. If you're not subscribed to my channel, please subscribe, and have a nice day. Bye.